So I would like to begin looking at friction by exploring a mystery. This mystery happens in Death Valley. It's a true story. There is this broad, flat plain in Death Valley called the Racetrack Playa. It's called the Racetrack Playa because there are these strange stones that seem to be moving. And they don't just seem to be moving, but they actually leave these huge trails behind them, right? And it's very, very hard to capture the actual motion or these trails being created, right? But nevertheless, they do move. And the trails are very, very visible, okay? And this was a mystery for a very long time. And, many, many theories were explored. One of those theories was simply that, there's these winds that get funneled through the valley, and that actually creates enough of a wind load on the stones to push them along the valley floor, okay? Turns out this is far too simple of an explanation, and they have kind of locked it down, an explanation that's really cool and unexpected, and a little bit more complicated than we can analyze here with frictional forces. But I thought that I would add a video after this video of somebody explaining that mystery. But for now, I want to explore friction by looking at the simplest explanation, which is that it is actually these winds that are funneling in and creating a load, okay, on these stones. And the question is, what wind load, what wind force would actually be required to get these guys to move along the desert floor, okay? Well, to answer this question, we need to look at friction, okay? So imagine, if you will, that we have a fairly rough desert floor, okay? And imagine, if you will, that there's a stone there, right? And like every force problem that we've done so far, we start by drawing a free body diagram. Look at all the forces that are existing on this guy, okay? Well, what forces are existing? Well, we know it's got a weight, okay? And weight is always mg, okay? We know that it's resting on a surface and it's not falling into the earth, so we know that it must be balanced out by a normal force, n, okay? But if this guy's actually going to be moving, there must also be this, we'll call it F wind, right? So some kind of force due to the wind that's blowing on the stone, okay? And if there's a force in this direction, and we're finally dealing with the real world where there's actually frictional forces, we can't forget that there is going to be a static friction. I'm going to call it Fs for static friction, that is resisting that wind force, okay? And so, just like with all the force problems we do, to find this force, we need to do a Newton's second law analysis, okay? So we start by looking at summation of forces in Fx, right, in the x direction equals m times the acceleration in the x direction, okay? And the sum of the forces in y equals m times the acceleration in the y direction, okay? Let's take a look at this. Now, what is happening in the x direction? Well, we got a wind force in the positive direction, so I'm going to put my positive wind force there, right? And then we got this static frictional force in the negative direction, so I'm going to put negative static friction force, right? And just a reminder, the frictional force always opposes the direction of the motion, right? And so if the wind wants it to move this way, static friction is going to be pushing this way, okay? And so we want the wind force just necessary to overcome the maximum static friction, right? So what is basically the FW so that it equals FS, right? And if those guys are equal, this guy is just going to be zero, right? We want to find out just the very minimum wind force to get this going, okay? And in that case, they're going to be balanced, all right? So we start there. And then we realize, wow, okay, well, the wind force then just has to be equal to the static frictional force, right? But the static frictional force, as we know, is mu times the normal force. But we have a problem here, because we don't know what that normal force is, okay? So we pause because we're kind of stuck, right? But we know we have more information. And just like with kinematics, sometimes you can get that other information from the other dimension. So let's see what's going on in Y. Okay, well in Y, I have a normal force going up. So I put my N for normal force. And I have weight going down. So minus mg, right? And so far as I can tell, this stone isn't randomly flying up into the air and it isn't falling through the earth. So these forces in Y are balanced, and that's just going to be 0 right there, right? Okay, this tells us that our normal force is actually just equal to our weight, or mass times gravity. And how convenient is that? Because now I can just take this normal force and put it in over here. And that means that my wind force is just equal to mu times m times g. Okay? Now, I can't lie to you. I forgot my computer over there. And it has the value for mu, and it has the value for m. I know the value of g, right? But I'm going to encourage you all right now to put in that value that that problem says, and this value for m that the problem says. I believe it says 1 pound, so you're going to have to convert pounds into kilograms. I do remember that much, okay? And then g is obviously 9.8. Put those all in, and this will determine for you what wind force would be required to move this rock, okay? So now if a geologist who's studying this in Death Valley came to you, you would be able to be like, oh man, I can do an analysis to tell you exactly what wind force is required to move this stone, okay? And then you'll get paid, like, I don't know, like $50,000 or something, okay? For this much work. That's how important physics is, okay? So plug that in, and I will meet you in the next video when we take friction to the next level.